Good afternoon, class. We're here today to start with Chemistry 311, Physical Chemistry 1. You know, this course is 3 units. And Module 1 of the class material has been divided into Modules 1.1, 1.2, and 1.3 for the purpose of this online video. So it's going to be easy, short videos for us to be able to understand the concepts and then compare with the explanations here and what you have in that class material. And of course, if you have any questions, remember we'll have a class group. Ask your question in the class group and we'll look at it and explain further. So this module is the beginning of Physical Chemistry 1, Chemistry 311. My name is Professor Engineer J.C. Iwe. We're going to take up this lecture following this outline: introduction, conditions for chemical equilibrium, law of mass action, illustrations, and then we conclude. Now, by way of introduction, as chemical reactions occur, the reactants are used up in the formation of the products. Yeah, of course, as reactions, let's say A and B is reacting together to form products. As time proceeds, because the reaction is going on, the quantity of A and B that we started with will start depreciating, we start reducing because there's formation of products. And of course, the quantity of products will be increasing. 2, at some point in a reversible reaction, the products also react to form the initial reactants in a backward reaction. Of course, now we're talking about a reaction that is reversible. Remember, we have different kinds of reactions: reversible reactions, irreversible reactions, parallel reactions, consecutive reactions, and so on. But we're interested in reversible reaction. Reversible reaction means as the reaction is proceeding, at some point, the products will start reacting again to reform the reactants. And that's where you have a double arrow showing forward reaction and backward reaction. 3, thus, chemical equilibrium is considered as a state of system in which the rate of disappearance of the reactants to form the products is exactly equal to the rate at which the products interact to reform the reactants. So when the forward reaction is equal to the backward reaction, we say that the reaction has reached equilibrium. The rate of formation of products is equal to the rate of formation of the reactants. So we have forward and backward reaction. 4, therefore, it is expected under these conditions that no perceptible change can be detected in the system. Now, what that means is that there won't be any change in the concentration. Imagine that we have a class of 50 students, and I decide to say, okay, 25 stay outside, 25 stay inside. And I now want everybody, people to be coming in one by one as they are leaving, as one person is leaving, one person is entering. So if you see at any moment, one person inside leaves and goes outside, another person outside comes in, it's still 25, 25. That's what this equilibrium is talking about. That we will not see any change in the concentration at that equilibrium. Although there is a dynamic thing happening, but you won't be able to detect the change in concentration. 5, consequently, the net effect is an apparent state of dynamic equilibrium. That's what we said. Then 6, thermodynamically, we have homogeneous and heterogeneous equilibrium. We won't go further, but let us note that homogeneous and heterogeneous, when we talk about homo, remember, everything is in the same phase. So homogeneous here means that all reactants and products are in the same phase. Or heterogeneous, when you might be having a reactant in a solid phase, product in liquid phase, or one reactant in solid phase, another reactant in gaseous phase, product is in another phase. That's when we talk about heterogeneous equilibrium, when they are not in the same phase. But when all the reactant products are in the same phase, even if in terms of catalysis, if you have the catalyst also in the same phase, we'll start talking about homogeneous catalysis and heterogeneous catalysis. Now, conditions for chemical equilibrium. Now, there are conditions that we will observe and we say we have chemical equilibrium. Of course, again, we are talking about homogeneous and heterogeneous equilibrium. Now, using the second law of thermodynamics, any spontaneous or natural process must be accompanied by an increase in the total entropy of the system. Remember, entropy is a measure of the degree of disorderliness. So for a reaction to proceed, the entropy must increase. So for two species A and B, SB minus SA is equal to the change in entropy, which is equal to 0. So we use this to now obtain 5 conditions for chemical equilibrium. The first one is under entropy. If we combine first and second law, we'll have TdS minus the E minus P dV equal to 0. Therefore, change in entropy at constant internal energy and volume must be equal to 0. Again, for condition 2, in terms of internal energy, the change in internal energy at constant entropy and volume must be equal to 0. These are combination of first and second law equations. Again, for condition 3, we know that dPV, this is multiplication of two constants. I mean a differential of two constants. We have dE equal to the TdS minus dPV plus the P. We'll now solve and get the enthalpy. So in terms of enthalpy, change in enthalpy at constant entropy and pressure must be equal to 0 under equilibrium. We also go for condition 4 in terms of the Helmholtz energy, and we must note that condition 4 and 5 are very important. If you look at the other conditions, we have entropy in the 3 of them, and it is very difficult for us to measure entropy. But in condition 4 and 5, we have temperature, volume, temperature, and pressure. So it's easy for us to monitor temperature and volume. It's also easy to monitor temperature and pressure. So condition 4 says that the change in Helmholtz free energy at constant temperature and volume must be equal to 0. Condition 5 also says the change in Gibbs free energy at constant temperature and pressure must also be equal to 0. And these 5 conditions gives us the conditions for chemical equilibrium. The law of mass action. The law of mass action relates the driving force for a chemical change to the mass of the active species involved in the reaction. And this law states that the driving force of a chemical species is proportional to the active masses of the reacting species. This is the law. It's based, when we look at this equilibrium now, look at it, the forward reaction AB gives CD. So the rate of forward reaction is directly proportional concentrations of A and B. Now in the reverse reaction, we have the rate proportional to concentration of C and D, because in the reverse reaction, C and D automatically becomes the reactant. So if forward reaction is equal to backward reaction, we can then equate this and we arrive at this equilibrium constant equation. The product of concentrations of the product divided by the product of concentrations of the reactant, and that gives us the equilibrium constant. And this equilibrium constant can be represented in 3 ways. 1 is activity, 2 is in terms of concentration, and 3 is in terms of pressure. Of course, pressure and concentration is the same, except that when we talk about pressure, we are referring to gaseous components. Okay, then we are trying to put up an illustration, very simple and smooth, equation and solution. You look at it, the dissociation constant, acetic acid in water is given by that, you're giving concentrations. So we use the equilibrium constant equation, substitute the concentrations of the species, and we'll get the equilibrium constant in terms of concentration. Illustration 2, we're also given the reaction, and we're told that the equilibrium constant is equal to 4. and we're given the equilibrium concentration of one species and we're told to find the other. We substitute and we calculate. Module 1.1, we've looked at conditions of chemical equilibrium, the law of mass action, and then looked at 2 illustrations to explain this concept. Thank you very much and see you in the next class.